Hello there, welcome to your fifth webinar. In this webinar, we will talk all about feature extraction and all of the different methods that you can extract features. In your course, you have actually a part for feature extraction and embedding, but in that part, there is no actual any Jupyter notebook that it will teach you exact step by step you can extract a feature. So in this webinar, our goal is to actually go deep more into the coding part. And more specifically, we will go through 6 different parts of the feature extraction. So what is feature extraction? After that, we got any type of text. At the very start, we need to apply pre-processing. And before actually put those data into our model, we need to also extract some features. And what type of feature we need to extract, it depends on what type of problem we are trying to solve. And in this Jupyter notebook, you will have some idea how it works and in what type of problem you have to use it. So let's get started. The first type of feature extraction that we are going to talk is called bag of words. What is bag of words? Bag of words means that if we have any type of documents, which is just a text that we have, what we want to do is we want to get all of the unique vocabularies in it. And also note that the vocabularies that we want is after pre-processing. So we get a document, we pre-process it, and we get all of the unique words. This is called bag of words, as simple as that. So let's actually see the data we are going to use. This is our text, which I also got this from the course. This is the same thing as this, and what we want to do is to convert all of our corpus or our text into a vocabulary. So this is our text, and like always we will write a pre-processing function, pre-process text. In here we will just get a list of text, since in here, as you can see, list of text, we want our corpus. So at the very start, we will lowercase the text, like always. Text, list of texts, dot lower. Then we will remove the punctuation, which we will use a regular expression library, so let's import it. Okay, text, we will sub, now we want to say keep all of the lowercase, keep all of the uppercase, and also keep all of the numbers. If it was other than that, then we will replace it with an empty string. And also we want to apply this to our text. The next step in our pre-processing is to tokenize our text. So converting to tokens. Let's use an NLTK from nltk.tokenize. Okay, let's see what is the problem. Oh, sorry, I forgot to say word tokenize. Okay, let's tokenize our text. We can say tokens is equal to word tokenize, which we just imported it. Now let's remove all of the stop words. And before that, let's import the library. from nltk.corpus import stop words. Okay, now for removing the stop words, we want to iterate through all of the tokens, and if it was inside the stop words list, then we will not append it. So let's say tokens, we are going to have a list, we will iterate through the tokens, and if iToken, we only accept iToken if it's not inside the stop words. And we want to specify that stop words is English, because NLTK also have stop words for other languages as well. Okay, now we have our tokens. Then we want to apply stemmer. So before that, let's import the library from nltk.stem. Import porter stemmer. Now in here also we want to iterate through all of the tokens and apply the stemming. Say stemmed for I token in tokens. Then for each of the tokens we want to apply the porter stemmer I token. Now lastly we will apply lemmatizer. Lemmatized, the same. Now also remember that for lemmatizing our tokens, one time we have to apply it for the nouns, one time for the verbs. We cannot do it all together. So let's first import a library from nltk.stem, import wordnet lemmatizer. So like in stemmer, we want to iterate through all of the tokens, then apply the lemmatizer. iToken, tokens, wordnet, lemmatize, iToken. Also in here you can specify the part of speech. As I said, one time we will do it for noun and the other time we will put it for the verbs. Let's say verbs, and also we apply this to our lemmatized. Okay, now we can return this, which this was all the pre-processing step that we need to take. Return lemmatized. Okay, very good. Now our function is ready, and what we want to do is to apply this function to our text. So at the very start, what we want to do, as you notice, this is a list of strings. We can convert this into just one string instead of having a list of string. And it's very simple. We can say dot join. It will append all of the text to each other. Now let's actually take a look at it. How does it look? Okay, as you can see, the list of strings converted into just one single string. And then let's also apply this preprocessing function to it. We can say tokens preprocess text we apply the text to it. Okay, now let's take a look at the tokens. Print tokens. As you can see, we got our text and we applied pre-processing, and also we tokenize all of the text. So now the next step to get is actually all of the unique vocabularies, because as you can see here, there shouldn't be any repetition. There should be only unique values. And for getting the unique values, we can use NumPy. But before that, let's import it. And we can easily say vocabularies is equal to np.unique. And that is it. We just apply this to our tokens, and we will have our unique vocabularies. And if you notice, there is no repetition. For example, in here there's two twinkle, and in here there's only one. Or in here there's too little, there's just one. Okay, now we can have a documenter matrix. What does this mean is actually we have our corpus that we applied the pre-processing, and also we got the vocabularies. We have our corpus, and also in here we have all of our unique vocabularies. What we want to do is to count it. For example, in this sentence there's one little, then we put one in here. There's one house, then we put one here, and so on. And we will count each of the unique vocabularies into our corpus, and we put in a corresponding matrix. And this matrix is called documenter matrix. So let's start by writing the function of it. Say documenter matrix. For our parameter, we can have two parameters. First, let's say list of new sentences. We can also use the same corpus that we used before, and also our vocabularies. So list of new sentences are this corpus. Vocabularies are this, that we only want to get it as our parameter. At the start, we want to initialize the empty list, so we can append all of the documenter matrix to it. Let's say initializing an empty list for all the documenter matrix. List of documenter matrix, which is equal to a empty bracket. And also we want to iterate through our list of new sentences. For I new sentence, let's say in list of new sentences. And at the very start, for sure, we want to pre-process this I new sentence. Process the sentence. Okay, say new tokens, pre-process text, I new sentence. Okay, now we process our text. So now let's initialize a zero array for our vocabularies. That first we will initialize it with 0, then we will actually add 1 to it if the vocabulary was in the corresponding sentence. So let's say initializing a 0 array, which DTM, which stands for documenter matrix. You can say np.zeros, and we want this to be equal to the length of our vocabularies, because like we want this corresponding row, this corresponding row, this corresponding row, all of them are equal to the length of our vocabularies. Now let's iterate through the tokens, this new tokens that we have. Iterating through tokens. So for I token in new tokens, again we will have our third loop, which we will iterate through the vocabularies. Iterating through vocabularies. So let's also have index and use enumerate, so it will come handy. I vocab in enumerate vocabularies. And in here we want to do is to, let's say we want to add one if the tokens is inside the vocabularies, and in this way we will add all of the corresponding items. So add one if the token is inside vocabulary, and we can write it down simply by say I vocab if it's equal to I token. If this I vocab is equal to this I token, then we will just get this zero array in the corresponding index. We will just add 1 to it, and simply we just count it, and we will go out all of our loop, and we want to append the documenter matrix to the list of documenter matrix, this list that we initialize at the very start. Say append the documenter matrix to the list of documenter matrix. List of documenter matrix, which is this. We will append the DTM, this that we also added, and we count the vocabularies in it. Now we can also we can also convert this into a data frame, so have a better visualization of our stuff. Let's import the pandas as PD. Okay, we say convert to data frame. Let's again call it DTM pd.dataframe. And as our data, we are going to have a list of documenter metrics in here. And as our index, we are going to have a list of new sentences inside another list. This is necessary because otherwise it will show error. It's important the data type you use is to actually matches to the other type of data set, data frame, data type. So let's also say column is equal to our vocabularies. Now at the very end we will just return this DTM or documenter matrix. So this is our corpus that we are going to use, or list of new sentences, which is one of the parameters also. Now let's apply this function to our list of new sentences. So we can say DTM documenter matrix list of new sentences here, and also vocabularies, which we did before. Did it in this part. Okay. Now let's take a look at our DTM. Okay, now as you can see, we went through all of this vocabulary and counted if the corresponding vocabulary is inside this text or not, and if there is, how many words are there. For example, if you see there's twinkle twinkle, there's two. We also counted two. And at the very end, if you like to learn more about bag of words, there are 3 great resources that you can actually go read. It is not necessary, but it actually can help you a lot. Okay, now let's go to the second type of feature extraction that we will learn. This feature extraction is called TF-IDF, which is short for term frequency and inverse document frequency. What in here we want to do is to actually in document term matrix divide each of these items in a sum of the whole column. Let me show you. If you sum this column, it will be 3. If you sum this column, this is 1. What it is in here we want to do is to divide each of the items to the sum of whole column, which is 3. Divide this by 3, divide this by 3, divide this by 3. Also divide all of this item by 1, all of this by 1, and so on. So we can simply just copy the document term matrix that we have, and we call it TF-IDF. Let's say dtm.copy. And in here we want to divide each of the items in our TF-IDF by its term frequency. Document frequency. Document frequency is the sum of the whole column. So at the very start we want to iterate through the column names. Say for index 1, since we are going to have 2 loops. Index 1, I column name enumerate TF-IDF dot columns, and let's get the column, corresponding column, the column we call it I call TF-IDF I location index 1, which in here we will iterate through all of the columns. And also let's get the sum, get the sum of column, I call sum, which we can just say sum I column. Okay, now let's iterate through again into our column. Iterate through items in a column. This time let's say for index 2 I item in enumerate I column. So at the first loop we will iterate through each of this column. At the second loop we will iterate through each of the items inside the column. So what we want to do now is to divide each item to the whole sum of column. So we can just say simply TF-IDF iLocation, index 2, which is each item or the row, and index 1, which is the column. And you want to say we want to divide this to the sum. I call sum, which we got it here. Now that is all we have to do to get our TF-IDF. If we take a look at it, you will see that each of the items got divided to its document frequency. For example, this was 1, all of the items got divided by 1. This was 2, all of the items got divided by 2. That's why we have 0 0.5, 0 0.5. It was 3, and in here we divided by 3, that's why we have 0 0.3333, and so on. And also this is extra resources if you like to learn more about TF-IDF. Okay, let's go to the third feature extraction, which is called one-hot encoding. What is one-hot encoding? In one-hot encoding, we will create a zero array, zero vector for each of the words, and we put one in a corresponding place. For example, in here, house, its place is here. We put one here. Lamp is here. We put one here. And in here, we just want to make a vector for each word, all 0 except 1, which is its place. So let's start by writing the function. In this function, we will get our vocabularies as our input. And at the very start, what we want to do is to create a zero array. So later on, we put the 1. But for now, we just want to have all zeros. Let's write this down. One hot encoded. np.zeros, and in here we want to, let's say we want the amount of length of the vocabularies for our rows and also for our columns. Okay, now let's also convert this to the data frame. Can choose the same name. Let me say pd.dataframe, and as our data we choose the one hot encoded in here, and as our index names we want to be vocabularies name. We have to put this on our, we have to put the vocabulary into a list, vocabularies, and also we want to have the columns names of vocabularies again. And in here now we have a data frame that each column and each of the rows are named after the vocabularies. So let's set one if the word exists in the corresponding place. For doing this, we have to iterate through our vocabularies. Then, in its place, we put 1. Let's first iterate through it. Vocab in vocabularies. And in our what-hunt encoded data frame, we want to find the location of the place, which is ivocab, which is house, house, lamp, lamp. We want to find these places. Then when we found this, we want to assign 1 to it. And that is it. We can now just return the what hot encoded. Okay, now also let's apply this function to our vocabularies. Encoded, encoding. We put our vocabularies. And also let's see it. Okay, as you can see, in here we have house, house 1, lamp, lamp 1, star, star 1. This is 1, the rest is zeros. And for example, let's say we want to take the vector of stars. We want to have the one hot encoded of one hot encoded version of it. You can say one hot encoded location. You choose a star, which it will take this row, and then we will say values. Now we have a vector of zeros, which we have only 1 in its corresponding place. And that is it with the hot encoding. And if you're interested, you can learn more in the resources part. Okay, let's go to the next part of this Jupyter Notebook, which is about word embedding using word2vec. As this sentence implies, we want to convert each word in our corpus to a vector of numbers. And word2vec can be divided into architecture. One is continuous bag of words, and the other one is skipgram. In this part, we will use continuous bag of words, and I will exactly show you how you can use a skipgram too. So it's a very small change. And one of the cool things that you can do with this word2vec is to find the most similar words or find the most dissimilar words in your dataset. And this is exactly what we are going to do in this part. So let's start by fetching a data from a website, and then we will apply all of the pre-processing and also word2vec to it. So first let's import the library, URL lib, port request. Then we want to fetch a Wikipedia page, and we can say request .url open. Also be careful to add the .read at the very end of this line. Okay, next we want to remove all of the HTML tags. We will use beautiful soup. You can say beautiful soup data HTML5 lib. And also there's a lot of data into our web page that is very unnecessary. For example, this part or this part or this part. So we really do not want to take that. The only thing that we want to take is paragraphs. That is all we want. It is simply, we can say paragraphs data, and we use data.find all, and we put p. Now we have all of the paragraphs. However, now we have a list of beautiful soup type that we cannot really work with it. What we want is a list of strings, not list of beautiful soup type. And we can convert it by first iterating through the paragraph. Then we will get the text of it. Then also we want to delete all of the empty places. Okay, now we have our data. Like always, we will apply pre-processing to it. say pre-processed tokens. Now, same as before, we want to since this is a list of strings, we want to iterate through each of these strings, then apply this pre-processing to it. So for I in article, pre-process I. Okay, now we have our pre-processed form. We can take a look at it. As you can see, this is the list of lists, and inside each of them are our tokens. Next, we want to apply the bag of words to it. We will use a library. First, let's import it from gensim.models. Import word2vec. Also, let's say word2vec. Now in here at the start we put our pre-processed tokens. Then there's SG, which if in here put 0, we will compute continuous back of words. If you put 1, we will compute skip grams. So since we want to continuous back of words, we put 0. Then also define size 200. Window can say 5, and also min count. Since we don't want to count every single word, we want to be at least 2 words. Then we put iteration of 5. Now we can get all of the vocabularies by one line of code. We will say word2vec, the WV, which is word2vec, and vocab. Now we got all of our vocabularies. If you take a look at it, you will see that this is a dictionary, that each key is one of our vocabularies, and its values is a vector of values. Now you cannot see it, but let's take a look at how it will look. Word2vec. Let's say we want to get the word artificial. I put it like this because this is after stemming and the lemmatized form. So this is the type of vector you will get for each of the word. And let's say we want to get all of the similar words that are similar to intelligence. So let's sim words, word2vec, WV, similar by word. You can put this intelligence in it. And also we want to show top 10 words. And this is our top 10 words. The words that are similar to intelligence are AI, use, machine, human, ethic, compute. Of course, this can be not perfect because of our data set. It was a little bit small, and if you use a more perfect data set, of course the result's gonna be better. And now let's say we want to get all of the words that are similar to humans but dissimilar to machine. So let's say result word2vec, WV, most similar. positive means words that are similar, which we put human, and negative are the words that are dissimilar, which we put machine. And this is our result. So now let's actually visualize our word-to-vec vector. Let's start by retrieving all of the vectors. We can say word-to-vec, and we will get all of the vocabularies. So now let's apply the PCA to our retrieve vectors. But first let's import it from scikit-learn. From scikit-learn dot decomposition position import PCA. Also let's also import matplotlib dot pyplot as plt, and also matplotlib inline. Okay, sorry, matplotlib. Okay. So first we will initialize it, PCA and components 2, and now we will fit and also transform it. PCA fit transform. Apply X. Okay. Now the only thing that we have to do at the end is just actual plot it. At the very start, let's change the size of it so we make it big enough for seeing. Then let's make a scatter plot, which will get the result in here. The first one, the second. Okay, now let's get the words. Word-to-vec wv.vocab. Now we will iterate through the words. Now let's also annotate each of the scatters with their actual names. So we don't want it to be just a dot. Okay, this might take a while. Now let's wait. Okay, now we plotted all of our words, and if you notice the words that are actually similar, they are more near to each other. And that was from the plotting. If you needed any further resources, check it out here. Okay, let's go to the next part of this Jupyter notebook, which is about GLOV, or Global Vector for Word Representation. So in here we will use a dataset from Stanford. I put the link here. You can go click on it. And in here there's already some pre-trained word vectors. We will download the least heavily dataset, which is around 800 megabyte. They also have like 1 gigabyte, 2 gigabyte. You can download all those, but for now we will use this. So let's start by importing. Say from gensim.models import keyed vector, and when you downloaded it, there's going to be a file that in this file we will, let's say file name, we put the path on it. Glove is the first file, and then we say okay, then we say model keyed vector dot load word to vec, and then we put the file name, and also we want to file name, and we also put the binary to false. Okay, one very cool thing that you can do is to say, for example, king minus man plus woman is what? So this is queen. There's also one picture here. Okay, as you can see, man, woman, there's a vector, and so king and woman. And what we want to do is say king minus man plus woman, which it should be queen. So let's say result model dot most similar positive woman and king, negative men. We also have to put this in an empty bracket, and then we want to show only first item. Print result. As you can see, it is queen already. So, and if you need any further resources, you can click on here. And the last part of this Jupyter notebook is about t-distribution stochastic neighbor embedding, which we will visualize the MNIST fashion dataset. So let's start by importing the MNIST fashion dataset itself, which Keras already have it. Datasets, import fashion MNIST, and you can load the dataset by saying xtrain, ytrain, also xtest, ytest. You will put it equal to fashion MNIST and load dataset. Let's also take a look at the shapes. Training set shape. And also test set shape. Test set. Xtest. Okay, as you can see, we have around 60,000 for our training set and around 10,000 for our test set. Now let's just work with a subset of it just to give some speed to it. We will call it X subset, and we will take only the first 200,000. We will do the same thing also for the Y. Now let's visualize the first two items in our training set. Let's say PLT subplot. 1 to 1, which we are going to have 1 row, 2 column, and it's going to be first item, ability show, subset, first, also C map of gray. Called the second item here. So this is our first 2 images in our training set, and before we use our training set and put it in our PCA, we need to reshape it, because in here we should have only 2. First should be the number of images, and the second part, it should be reshaped, that it should be just 1 vector. So let's reshape this. Subset, call the second here x subset, and we say reshape 200,000, 28 multiplied by 28. And if you take a look at the shape of it, this is exactly what we want. We converted 20,000, 28, 28 to 20,000, 28 multiplied by 28. So in our, if you go to the scikit-learn documentation for visualizing the t-SNE, it will tell you before actually applying this, apply PCA to it, and then apply t-SNE to it. So we will first import the library from scikit-learn, decomposition, import PCA. PCA and component, let's say 50, PCA result, which we are going to fit and transform, PCA fit transform x subset. Okay, now let's also import library for t-SNE itself from scikit-learn dot manifold import c. Okay, now let's go below. So now at the end we will apply the t-SNE to our PCA. We call this PCA t-SNE. Transform, we will apply to this. Okay, until it computes, I will import another library which is called helper. This is for visualization, which I put it in the same directory as your Jupyter notebook. We will import the fashion scatter. And also let's import some extra libraries. Import numpy as np, import matplotlib, as plt, and also matplotlib inline. And for the visualization, the only thing you have to do is say fashion scatter, which we just imported it, and put this here, and also our y subset, and that is it. Say plt.show. Okay, until it computes, we have to wait for a couple of seconds or minutes, and we'll see the final result. Okay, as you can see, this is our final version of the visualization. Thank you very much. I hope you enjoyed this webinar.